So any questions about, are there anything we've been doing in the lectures or homework problems? Yes, no? So there's a homework due today. Maybe I'll start by going over the problems. So homework 7 is problems on group theory. And let's take a look. So suppose we take G to be the group which is the cyclic group of order 4. So in this group, this is generated by the element A. That means every element of the group is a power of A, and A to the 4th power is the identity. In fact, if you wanted to look at the multiplication table for the group, this is EA, A squared and A cubed, EA, A squared and A cubed. So multiplying anything by the identity gives you the anything. A times A is A squared, A times A squared is A cubed, A times A cubed is A to the 4th, which is the identity. A squared times A is A cubed, A squared times A squared is A to the 4th, which is the identity, and A squared times A cubed is A to the 5th, but A to the 5th, which is A to the 4 plus 1st power, is A to the 4th times A to the 1st power. That's E times A, which is A. A cubed times A is A to the 4th, it's the identity. A cubed times A squared is A to the 5th, which we just saw is equal to A. And A cubed times A cubed, that's A to the 6th. That's A to the 4 plus 2, so that's A to the 4th times A squared. A to the 4th is E times A squared is A squared. So that's the multiplication table for the cyclic group of order 4. And if you want to compare it to the addition table for the additive group of integers mod 4, what does that look like? 0, 1, 2, 3 are the congruence classes. 2 plus 1 is 3, 2 plus 2 is 4 is 0, 1, 0, 1, 2. And if you look at this and if you compare the exponents of A in this table, this looks just like the exponents. The exponents here, E is A to the 0. This is 8, 0, 1, 2, 3. This is 3, 0, 1, 2, 3, 0, 1, 2. So you can see directly from the multiplication table that this group gamma, the cyclic group of order 4, is isomorphic to the additive group of integers mod z. And the function from G to Z mod 4Z, that's a homomorphism and 1 to 1 and on to, is given simply by f of A to the power J is the congruence class J plus 4Z. This is the explicit isomorphism. So this is sort of background to the problem. It's just understanding the group. Any questions about this so far? Okay, well, in this group, if you look at the elements E and A squared, you see it's closed under multiplication. In fact, if we were to consider the subgroup H contained in G, H equal to the identity and E squared, what's the multiplication table for these elements? E A squared, E A squared. E times E is E, E times A squared is A squared. A squared times E is A squared. A squared times A squared is A to the fourth times the identity. So you can see that this is closed under multiplication, contains the inverse of each element, because E times E is E, the inverse of the identity is the identity. A squared times A squared is E, so the inverse of A squared is A squared, right? E inverse equals E. A squared inverse equals A squared. And of course, E is in this set. So this is clearly a subgroup. And what are the left cosets? So the left cosets of H, well, superficially, you have E times H, A times H, A squared times H, and A cubed times H. Right? This is everything of the form X times H, where X is in the group. That's the definition of the set of left cosets. So EH, this just means E times, I don't know, H for everything in H. That's the definition of the coset. This is E times E and E times A squared. So that's just E and A squared, which is H. So E times H is H. And also, if you take A squared times H, this is A squared times E and A squared times A squared. A squared times E is A squared. A squared times A squared, A to the fourth is E. So this is also equal to H. So these two left cosets are the same, and they equal H. What is the left coset A times H? This is A times E and A times A squared. That's A and A cubed. That's just what it is. And what about A cubed times H? That's A times, that's A times A cubed times E and A cubed times A squared. A cubed times E is A cubed. A cubed times A squared is A to the fifth, and A to the fifth is A. So these two are also equal. So the set of left cosets consists of H and AH, the two left cosets. What is the index? Well, G mod H is just the cardinality of the number of left cosets, that's 2. The two left cosets. And you could also, if you like, check this using Lagrange's theorem. The index of a subgroup H in the group G is the order of J over the order of H. The group G has 4 elements. The subgroup H has 2 elements. And the quotient is 2. Okay. Questions about this? Yes? No? What about problem 2? In this case,
Professor,
yeah.
I would like to know which one is the index here.
What is the index?
Yeah.
The index, this is the index. The index, this is the notation, square brackets G colon H. This means this is the number of left cosets. That's what the index is. The index of a subgroup in a group. That's the definition. And Lagrange's theorem says that for a finite group, the index is the order of the group divided by the order of the subgroup.
Thank you.
Okay, in problem 2, the group is the symmetric group S4. Someone asked, what is A? This is, we started with, if you look at the homework, the group G is this group, cyclic group of order 4, generated by the element A. So the group consists of 4 elements, E, A squared, and A cubed. That's what A is. A is the generator of the group we're talking about. And the 2 left cosets of the subgroup, this left coset H generated by E, and the left coset generated by A. Okay, so problem 2 involves a lot more work because we're looking at the group S4. And what is the order of S4? What is the cardinality of this group? Can someone tell me? So we spent a lot of time talking about symmetric groups. So you should know, if you take the symmetric group Sn, what is the order? So when n is equal to 4.
It will be 1.
What?
It will be 1.
The group is order 1. That means it only has 1 element. It just contains the identity. But this is the set of all permutations of 1, 2, 3, 4. And you know there are a lot of permutations, not just 1.
So maybe 24.
Exactly. It's 4 factorial. 1 times 2 times 3 times 4 is 24. So this group has order 4. And we look at the subgroup H. It's the cyclic subgroup generated by the cycle 1, 2, 3, 4. And just for notational simplicity, let me call this sigma. So sigma is the cycle 1, 2, 3, 4. So H is the cyclic subgroup generated by sigma. How do you write sigma in standard form? In the standard form for a permutation, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1. That's what sigma is. And When you have a cycle, 1, 2, 3, 4, this cycle has order 4. Sigma to the 4 is the identity. And this cyclic subgroup consists of E sigma, sigma squared, and sigma cubed. I mean, again, I'm not going to do it, but you should be able to do this. Here I wrote sigma as in standard form. You should be able to write sigma squared and sigma cubed in standard form, right? That you have to know how to do that. And we want to compute the left cosets. This is the problem. Compute the left cosets. The group S4 mod H and the index, that is the number of left cosets. In fact, this we can do right away. So by Lagrange's theorem, the index of the subgroup is the order of the group divided by the order of the subgroup. The order of the group is 24. The order of the subgroup is 4. Right? 1, 2, 3, 4. The order of H is 4. And 24 over 4 is 6. So when you calculate the left cosets, they're going to be 6 of them. And when you're calculating your left cosets and you get 6 different ones, you can stop because you know that's all there are. Any other questions about this? This is what you know in order to start the problem.
Professor,
Yeah, go ahead.
can you explain the part you're saying that the sigma square equal to the identity?
It's not. In this group, it's not.
No, you write something there, the sigma, when you try like to write it.
Sigma to the 4th.
Yeah.
You want to know why that's the case?
Yeah.
Okay, well, you can see it in 2 different ways. You can draw a picture. 1, 2, 3, 4. What does sigma do? It sends 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. That's sigma, right? If you write it in standard form, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1. What is sigma squared? That's when you compose sigma with sigma. So 1 goes to 2, and then 2 goes to 3. So for sigma squared, 1 goes to 3. What about 2? Sigma sends 2 to 3, and then sigma sends 3 to 4. So 2 goes to 4. What about 3? Sigma sends 3 to 4, and then 4 to 1. So 3 goes to 1. And what about 4? Sigma sends 4 to 1, and then you apply sigma again, you end up at 2. So this is sigma squared, which is really just the product of 2 transpositions, 1, 3, and 2, 4. So this is sigma squared. What is sigma cubed? You apply sigma 3 times. So 1 goes to 2 to 3 to 4. 2 goes to 3 to 4 to 1. 3 goes to 4 to 1 to 2. 4 goes to 1 to 2 to 3. That's sigma cubed. As a cycle, this is 1 goes to 4, goes to 3, goes to 2, goes back to 1. And what is sigma to the 4th? Well, this is sigma squared times sigma squared. Sigma squared sends 1 to 3, and then sigma squared again sends 3 back to 1. Or if you look at this, go 4 times around the loop, 1 goes to 2 to 3 to 4 to 1. 2 goes to 3 to 4 to 1 to 2. Everything goes all the way around the loop, and sigma to the 4th is the identity. So here I've written all 4 of these permutations in standard form. That's the subgroup H. It's a cyclic group of order 4. Okay. Any questions about this? This is just so we can start the problem. We haven't started the problem yet. The problem is to compute the left cosets. So we want the left cosets. That's 4 mod H. So of course, one left coset is E times H, which is H. That's always a left coset. What's another left coset? Well, you have to try different elements of S4 times H. So suppose we let H, for example, be the transposition 1, 2. So then what is XH? Remember, H consists of E sigma, sigma squared, sigma cubed. So you multiply everything on the left by X. This is 1, 2 times E, 1, 2 times sigma, 1, 2 times sigma squared, 1, 2 times sigma cubed. Of course, 1, 2 times the identity is just the transposition 1, 2. But each of these has to be calculated. What is 1, 2 times sigma? That's 1, 2 times 1, 2, 3, 4. This is the product of these permutations. Let's write it in standard form. 1 goes to 2, 2 goes back to 1. 2 goes to 3, 3 goes to 3. 3 goes to 4, 4 goes to 4. 4 goes to 1, 1 goes to 2. So this permutation is this in standard form. This is actually the cycle. 2 goes to 3, 3 goes to 4, 4 goes back to 2. That's 1, 2 times sigma. It's 2, 3, 4. What's 1, 2 times sigma squared? Well, what is sigma squared? I actually calculated that. Sigma squared is 1, 3 times 2, 4. So this is 1, 2 times 1, 3 times 2, 4. What is that in standard form? Composition of functions means you go from right to left. 1 goes to 1, 1 goes to 3, 3 goes to 3, 1 ends up at 3. 2 goes to 4, to 4 to 4. 3 goes to 3, 3 goes to 1, goes to 2. 4 goes to 2, 2 goes back to 1. So 1, 2 times sigma squared is this. 1 goes to 3, goes to 2, goes to 4, goes back to 1. So this is the cycle 1, 3, 2, 4. And what is the last permutation in this coset? 1, 2 times sigma cubed. This is 1, 2. What is sigma cubed? Let's go back and take a look. Sigma cubed is the cycle 1, 4, 3, 2. So what is that in standard form? So I want you to do it right now. What is the product of these two permutations? This transposition times this 4 cycle. So you need to work it out. Tell me what it is.
Professor,
Yeah.
I got something. I don't know if it's correct. I got 4213.
So sorry, what did you get?
4213.
So you're saying 4 goes to 2? So if you write it in standard form, what's in the second row? 1 goes to what?
4. 1 goes to 4.
Okay. 2?
2 goes to 2.
Excellent. 3?
3 goes to 1.
Yeah.
And 4 go to 3.
Excellent. Because if you follow this around, 1 goes to 4, goes to 4. 2 goes to 1, and then goes back to 2. 3 goes to 2, and 2 goes to 1. 4 goes to 3 and stays at 3. So this is a 3 cycle. 1 goes to 4, 4 goes to 3, 3 goes back to 1. So the left coset, 1, 2H, is that. Let's compute another left coset. Suppose I take X to be 1, 3, and I want to compute XH, this left coset. So this will be 1, 3 times the identity, 1, 3 times sigma, 1, 3 times sigma squared, and 1, 3 times sigma cubed. So it's very important to learn how to do simple calculations in group theory. So you need to calculate this. I mean, you know, obviously, that 1, 3 times the identity is just 1, 3. What's 1, 3 times sigma? That's 1, 3 times, what was sigma? Sigma is the cycle 1, 2, 3, 4. What is this if you write it in standard form? 1 goes to 2 goes to 2. 2 goes to 3, 3 goes to 1. 3 goes to 4 goes to 4. 4 goes to 1 goes to 3. So this is the cycle. This is the product of 1, 2, the transposition 1, 2 times 3, 4. That's what this is. What is 1, 3 times sigma squared? Well, that's 1, 3. What is sigma squared? Sigma squared is 1, 3 times 2, 4. 1, 3 times 1, 3 is the identity times 2, 4. So this is just the transposition 2, 4. And what is the third element of this coset? 1, 3 times sigma cubed. That's 1, 3. What is sigma cubed? Sigma cubed is the 4 cycle 1, 4, 3, 2. So in standard form, what is that? 1 goes to 4, goes to 4. 2 goes to 1, 1 goes to 3. 3 goes to 2, 2 goes to 2. 4 goes to 3, 3 goes back to 1. So this is 1, 4, 4, 1, that transposition, and 2, 3. So this is the product of two transpositions, 1, 4, and 2, 3. So we know by Lagrange's theorem that the index of H in S4, that is the number of left cosets, is 6. And here I found 3 of them already. And you just keep computing until you have all 6.
Professor?
Yeah.
Yeah. How did you choose your X? Because the first one you choose 1, 2, the second one 1, 3.
I'm more or less choosing them at random until I get 6 different cosets. And I know there are only 6 cosets. I also know that cosets are disjoint from each other. 2 different cosets have no elements in common. So for example, if the coset EH consists of E sigma, sigma squared, and sigma cubed, then I don't need to choose any of these other 3 elements for a left coset, because the left coset will automatically be the same as this. Here, the left coset.
Professor, I can see it.
No, all I'm saying is, for example, left cosets are either disjoint, they either have no elements in common or they're exactly the same. So for example, this left coset contains these 4 elements. If I were to look at the left coset generated by, for example, 2, 3, 4, that would include 2, 3, 4. That means it would be the same as this. So once I have a left coset, I can, like for example here, 4 elements. I don't need to try any of, there are only 24 elements in the group. I don't have to try any of these 4 elements again, because I'm not going to get a new left coset. Here in this left coset, it has these 4 permutations. I don't have to try any of these because I know I'll get exactly the same left coset. Here, I have another left coset. I have 4 elements. I don't have to try any of them again. So already from 1, 2, 3, from these 3 left cosets, I've accounted for 12 elements of the group. If I want to try another left coset, just pick something that's not in any one of these 3. For example, I could take the transposition let's see, here I have the transposition 1, 2. Here I have 1, 3. Here I have 2, 3. Sorry. This is 1, 4 times 2, 3.
We don't have 1, 4.
Right, we don't have 1, 4. So let me just do 1, 4, and we should see we get a completely new left coset. So suppose I take the transposition 1, 4 times h. So that's 1, 4 times the identity, 1, 4 times sigma, 1, 4 times sigma squared, and 1, 4 times sigma cubed. So this is equal to 1, 4 times the identity, 1, 4 times 1, 2, 3, 4, 1, 4 times 1, 3, 2, 4, and 1, 4 times, I think it was 1, 4, 3, 2. So I just have to calculate each of these. Of course, this is just 1, 4. What is 1, 4 times 1, 2, 3, 4? So I'll start by writing in standard form. 1 goes to 2, goes to 2. 2 goes to 3, goes to 3. 3 goes to 4, 4 goes to 1. 4 goes to 1, 1 goes to 4. So this is the permutation. 1 goes to 2, goes to 3, goes back to 1. It's that 3 cycle. What is this? 1, 4, 1, 3, 1, 4. Sorry, 2, 4. So 1 goes to 1, goes to 3. 2 goes to 4 goes to 1. 3 goes to 1, goes to 4. 4 goes to 2 to 2 to 2. So this is the cycle. 1 goes to 3, goes to 4, goes to 2, goes back to 1. So this is 1, 3, 4, 2. And what is the last permutation in this left coset? 1, 4, 1, 4, 3, 2. 1 goes to 4, 4 goes back to 1. 2 goes to 1, 1 goes to 4. 3 goes to 2, 2 goes to 2. 4 goes to 3, 3 goes to 3. So this is 1 goes to 1, so don't forget that. 2 goes to 4, goes to 3, goes back to 2. So this is another 3 cycle, 2, 4, 3. So here I have another left coset. I now have 4 out of the 5, 4 out of the 6. And I can calculate the other 2. I just pick permutations that haven't appeared in any of these left cosets already.
Professor, so the permutation is supposed to contain only 2 elements.
I'm sorry, say that again, please.
I was asking if the permutation is supposed to contain only 2 elements.
I don't know what it means to say a permutation contains an element. What does that mean?
Because the first one you choose 1, 2, the second one 1, 3, and the third one 1, 4.
No, there's no I chose to do that, but there's no reason. You can choose anything.
So you can contain even 3 or 4 elements if I want.
Yes, yeah, sure.
Okay, I see.
I just thought it was easier to work with a 2-element one because it was slightly less calculation. But it's completely up to you. So really, you need to, if you're not following the calculations, you need to go back after class and look at the video and just see what's going on and make sure you can do them, because this calculation these are like the easiest problems on the test. I mean, it's not like a proof of anything, it's just computing something. Okay. So let me just write, there are two more left cosets. Of course, we know there's 6 altogether in this group, with this group and subgroup. Problem 3. So we want to prove the following thing. Prove that if H1 and H2 are subgroups of a group G, then H1 intersect H2 is a subgroup. So we need a proof. So if H1 is a subgroup, then the identity is in H1, because the first requirement of a subgroup is that it contains the identity. If H2 is a subgroup, then the identity is in H2. Therefore, the identity is in H1 intersect H2. The intersection of 2 sets is everything that's in both of them. If H1 contains E and H2 contains E, then the intersection contains E. So the first condition is satisfied. Subgroup has to contain the identity. What about being closed under multiplication? So suppose X and Y are 2 elements in the intersection. Then first of all, X and Y are in H1, and X and Y are also in H2. To say that X is in the intersection means of 2 sets, means X is in both of the sets. Similarly with Y. But H1 is a subgroup. So if X and Y is in H1, then the product is in H1. And if X and Y are 2 elements in H2, then XY is in H2. Which means XY is in the intersection. So if X and Y are 2 elements in the intersection, then the product is in the intersection. That's the second property that a subgroup has to satisfy. And the third property is that a subgroup contains the inverse of each of its elements. And again, the proof is very similar, that XB and X1 intersect H2. So then X is in H1, and X is in H2. If H1 is a subgroup and it contains X, then X inverse is in H1. If H2 is a subgroup and it contains X, then X inverse is in H2. So if X inverse is in both of these, so X inverse is in H1 intersect H2. So if X is in the intersection, X inverse is also in the intersection. And so again, you have to be very rigorous about this. The intersection, a subset of a group is a subgroup if it contains the identity, if it's closed under multiplication, and if it contains the inverse of each of its elements. So we're done. That's the proof. Any questions about this? What about problem 4? So you have to recall Lagrange's theorem. It says for a finite group G and subgroup H, the index of H and G is the order of G divided by the order of H, which is the same thing as saying that the order of G is the index of H and G times the order of H. But these are positive integers, and this says that the order of H divides the order of G. So one consequence of Lagrange's theorem is in a finite group, the order of a subgroup divides the order of the group. So suppose you take the symmetric group S3. What is the order of S3? Can someone tell me?
Six.
Yep, it's 3 factorial or 6. And 4 does not divide 6. So S3 contains no subgroup of order 4. S3 can only contain a subgroup whose order is a divisor of 6, and 4 doesn't divide 6, so there's no subgroup. Any questions about this? The proof of part B is similar. If you take the group S4, the symmetric group with 4 letters, that has 4 factorial elements, which is 24, and 5 doesn't divide 24. So S4,
Why is it 24?
what?
Why is it 24?
Well, so in general, for every symmetric group Sn, the order is n factorial. That means 1 times 2 times 3, the product of all the numbers up to n. So S4 is 4 factorial, which is 1 times 2 times 3 times 4. You multiply it out, you get 24.
Okay, thank you.
So the order of S4, that symmetric group, is 24. 5 does not divide 24. So S4 contains no subgroup of order 5. Any questions about this? Okay. Problem 5. We have the additive group of real numbers are. Everything on the number line. And on that number line, we have the subgroup Z of integers. So here we have an infinite group R and an infinite subgroup Z. But in everything we proved about groups and cosets, except for Lagrange's theorem was specifically for finite groups, but everything else applies to a group that's finite or infinite. So we have the left cosets R mod Z. So a typical left coset for any real number R, what is the left coset? It's x plus z. This is x plus n for all integers n. So we have x, which is x plus 0, x plus 1, x plus 2, x plus 3, x plus 4, and so on forever. And also x plus minus 1, which is x minus 1, x minus 2, x minus 3, x minus 4, and so on. So you actually want a picture of the left coset. Let's say this is 0, 1, minus 1, 2, minus 2, 3. Suppose I take an x, I don't know, maybe over here. That's my x. Then this is x plus 1. This is x plus 2. This is x minus 1. This is x minus 2. This is x minus 3. X minus 4. You can see it's just x minus 5. It's just this point and then translated by whole numbers to the right and the left. So for this number x, maybe x is pi. This is pi, pi plus 1, pi plus 2, pi minus 1. It's this infinite set of numbers. Okay? So you have a left coset for every real number x, no matter where it is on the number line. And part A, where you have to prove that R mod Z, which is the set of all cosets x plus z for all x on the real line from minus infinity to plus infinity, it's really the set of all cosets where in fact you just take x greater than or equal to 0 and less than 1. So every coset's of this form, and we want to prove in fact you can restrict the x just to the unit interval. So it's enough to pick a green x between 0 and 1, including 0 but not including 1. And the proof is as follows: that x be in R. Then you can write every number as an integer n plus a little fractional part where n is an integer, and maybe I shouldn't call it. So it's everything of the form y plus z, where y is between 0 and infinity, but I claim, in fact, you can restrict it to numbers between 0 and 1. so that y be any real number. So I can write y as an integer, n, plus x. N is an integer, and x is between 0 and 1. That is, for example, if I took y to be 7.2, then this is equal to 7 plus 0.2. That's my integer, and that's my sort of like part between 0 and 1. That's all I'm saying. Take any real number, it has an integer part plus a fractional part. And the fractional part is greater than or equal to 0 and strictly less than 1. So the number, so y is n plus x, and y is in this left coset x plus z, because this is x plus an integer for all possible integers. So x plus n is something in here. So y is an x plus z. So y plus z and x plus z, these two cosets have a non-empty intersection. There's something in both of them. And if two cosets have an element in common, they're the same. So y plus z equals x plus z. So if you look at the set of all left cosets of z in R, that's the same as the set of left cosets x plus z, where x is in the unit interval. So I just proved half of the problem. So we just proved that the set of all y plus z for y any real number is equal to the set of x plus z, where x is not any real number, it's just real numbers greater than or equal to 0 and strictly less than 1. And the second part of the proof is to show if x is between 0 and 1 and y is between 0 and 1, and x and y are different, so let's say x is strictly less than y, then x plus z and y plus z, these two cosets have nothing in common. Their intersection is the empty set. So let me just draw a picture of this so you can see what's going on. Here we have the unit interval. And I have two numbers in this interval. I have x and I have y, and x is less than y. Let me put the y in green and the x in red. So I claim that x plus z and y plus z are disjoint. So what is x plus z? It's x plus every integer. So it looks just like this. It's the sequence of points that just differ by 1 forever, that kind of arithmetic progression. And the elements in y plus z, you just take y and shift it by an integer. And all that's being said when you look at it with this pretty picture is that this sequence of points, the red sequence of points, and the green sequence of points, they never intersect. So why is that? How do we write down a rigorous proof? So let's give a proof by contradiction. Suppose there exist integers m and n such that something in this coset, x plus m, equals something in this coset, y plus n. So then x minus y is equal to n minus m. And what can we say about this? Well, first of all, if m equals n, then x equals y. If m equals n, they cancel, x equals y. And we know that's false, because x and y were taken to be different. So therefore, m is different from n. And if you have the difference of two integers, n minus m is at least 1. So if I have x minus y is n minus m, then the absolute value of x minus y is the absolute value of n minus m. This is greater than or equal to 1. But x and y are 2 points in the unit interval. So the distance between them is strictly less than 1. And I have this contradiction. 1 is strictly bigger than 1, which is absurd, which is impossible. So assuming that these two cosets have an element in common leads to a contradiction and absurdity, and therefore they have to be disjoint. End of proof. Right. Any questions about this? This is a very nice proof. Let's look at problem 6. So consider the permutation sigma in the symmetric group S5. And this is the permutation. 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, 5 goes to 4. If we write this as a product of disjoint cycles, this is 1 goes to 2 goes to 3, goes back to 1, 4 goes to 5. What is the order of sigma? So remember the definition, the order of an element X in the group G is the smallest positive integer n such that sigma to the n is the identity. If that never happens, if sigma to the n is not equal to the identity for all integers 1, 2, 3, 4, and so on forever, then we say that then the order of sigma is infinite. Sigma has infinite order. Okay. But in a finite group, every element has finite order, and we have to find it for this permutation sigma. So let's just calculate it. So sigma is 1, 2, 3 times 4, 5. And you have to remember the fact that disjoint cycles commute. That is. Well, these cycles are disjoint. This involves the numbers 1, 2, 3. This involves completely different numbers, 4 and 5. So what is sigma squared? Sigma squared is 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. These cycles commute. So this is 1, 2, 3, 1, 2, 3, 4, 5, 4, 5. I just reversed the order. And 1, 2, 3 times 1, 2, 3 is 1, 3, 2. And 4, 5 times 4, 5 is the identity. So sigma squared is just 1, 3, 2. Sigma cubed is sigma times sigma squared. That's 1, 2, 3 times 4, 5. That's, sigma is 1, 2, 3, 4, 5. 1, 2, 3 times 4, 5 times 1, 3, 2. These two commute because they have no number in common. 1, 2, 3, 1, 3, 2, 4, 5. What does this do? 1 goes to 3 goes to 1. 2 goes to 1 goes to 2. 3 goes to 2 goes to 3. This times this is the identity. So sigma cubed is just the transposition for 5. What is sigma to the fourth? Well, sigma to the fourth is sigma times sigma cubed. Sigma is 1, 2, 3, 4, 5. Sigma cubed is 4, 5. 4, 5 times 4, 5 is the identity. If this is correct, this is just 1, 2, 3. Just sigma. What is sigma to the fifth? Sigma to the fifth is sigma squared times sigma cubed. That's 1, 3, 2 times 4, 5. That's what it is. And finally, what is sigma to the sixth? Sigma cubed times sigma cubed. Sigma cubed is 4, 5. 4, 5 times 4, 5. That's the identity. So the smallest positive power of sigma, which is the identity, when we start calculating the powers of sigma, first, second, third, fourth, fifth, sixth, the first time we get the identity is with 6. So sigma has order 6. And that means the cyclic subgroup generated by sigma has order 6. Any questions about this? Okay. Problem 7. Well, problem 7 is just like the problem we already did. The order of the symmetric group SP is, sorry, the order of the symmetric group SP minus 1 is P minus 1 factorial. That's 1 times 2 times 3 times 4, all the way up to P minus 1. This is not divisible by the prime P. P divides a product, it divides one, if a prime divides a product, it divides one of the factors and doesn't divide anything smaller than itself. Therefore, SP minus 1 contains no subgroup of order P. By Lagrange's theorem, the order of a subgroup divides the order of the group. P doesn't divide P minus 1 factorial. That's all there is to it. Any questions about that? Okay, so in addition to left cosets, we also have right cosets. So we have a group G, a subgroup H, and the right coset, take an element X in the group, HX, is the set of elements that you get by multiplying every element of H on the right by the element X. So the right coset is everything in the form little h times x, where h runs through the elements of the subgroup. That's the right coset. And H mod G this is the set of right cosets. Remember, G mod H was the set of left cosets. But whenever you have a subgroup of a group, you have the left cosets and you also have the right cosets. And we want to prove, the first thing we want to prove is that H mod G, this is the union of all of the right cosets, and for all x and y in the group, either hx equals hy or hx intersect hy is empty. So these sets are either the same or they're pairwise disjoint. And another way of saying it is, therefore, the right cosets of H partition the group G.
Professor, can you move the paper?
to the right cosets partitioning the group. That's what we have to prove. It's completely analogous to the same statement for the left cosets. So the first part is easy because x, which is e times x, is certainly in the right coset xh, hx, because e times x is x. So that means the group is in fact the union of all of the right cosets. If every element x is in the coset hx. So what we have to show is that if x and y are in the group and hx equals hy, hx intersect hy is not empty, then hx equals hy. That is, if you have the right coset hx and the right coset hy, and if there's some element z which is in both of them, then in fact the two sets are the same. So suppose z is in the intersection. So then z in hx means z is equal to h1x for some element h1 in the subgroup. And z in hy means z equals h2y for some h2 in the subgroup. So therefore, h1x equals h2y, which means x is equal to h1 inverse h2 times y, just multiplying on the left by h1 inverse, which means for all h in the subgroup, hx equals h1 inverse h2 times y. And this is an element of h, so this is in the right coset hy. So this element hx is in the coset hy for all h in h. So that means this whole right coset is contained in hy. And this is a completely symmetric argument. I also have from this, y is h2 inverse h1x, which means, just repeat this argument, hy is contained in hx. So if you have two sets, the first contained in the second contained in the first, then they're equal. And that's the end of the proof. We showed that if two cosets have one element in common, they're equal. And this proves that the right cosets of the group partition the group. Any questions about this? Okay. Good. This is fun. Not a lot of nice problems. That means this is problem 8. So next comes problem 9. So we have group G, the identity element E, and the subgroup H. So define a relation on G as follows. We say X is related to Y if XY inverse is an H. To prove this is an equivalence relation, that means a relation that is reflexive, symmetric, and transitive, and that the equivalence class of X is the right coset HX. Okay, so proof. First, we have to show that the relation is reflexive. Well, for all X in the group, XX inverse is the identity, which belongs to H. So X is related to X. Every element is related to itself, so it's reflexive. Suppose the relation is symmetric. What does this mean? It means that if X is related to Y, then Y is related to X. That's what we have to prove. So let's just do it directly. If X is related to Y, then XY inverse is in H. But this is a subgroup. So XY inverse inverse is in H because the subgroup contains the inverses of each of its elements. And what is the inverse of XY inverse? YX inverse is in H. Because XY inverse is YX inverse, which means Y is related to X. That's what I have to prove. So if X is related to Y, Y is related to X. And the third and last requirement for a relation to be transitive, let's recall what that means. If X is related to Y and Y is related to Z, then X is related to Z. That's what we have to do. But in this group, if you have elements X, Y, and Z, if X is related to Y, then XY inverse is in H. And if Y is related to Z, then YZ inverse is in H. And because H is a subgroup and it's closed on the multiplication, XY inverse times YZ inverse is in H. But XY inverse YZ, the Y inverse Y cancels. This means XZ inverse is in H, which means X is related to Z. That's what we needed to prove. So this relation is an equivalence relation. And let's recall the definition of an equivalence class. An equivalence class of a relation is so the equivalence class of X is the set of all Y such that X is related to Y. So what does this mean? So for X in the group, the equivalence class of X, it's all Y such that X is related to Y. But what is the relation? That means all Y such that X, Y inverse is in the subgroup H. This means the set of all Y such that X, Y inverse is equal to some element little h for some H in the subgroup. That's the set of all Y such that X equals HY for some H in the subgroup. And this is exactly the definition of the right coset. Maybe I should have written it like this. All Y, so the equivalence class of X is all Y such that Y is related to X. That's a better way to write it. So Y is related to X. That means YX inverse is in H. So this should be YX inverse equals H. Y equals HX. This is the equivalence class of X. That's a cleaner way to write it. In any case, that's the proof. All right, so this is just a bit more than half of the homework. I think I'll spend Wednesday actually going over the rest of this homework, and then we'll move on. But these are very important problems. I mean, this is exactly what you're supposed to learn in the first course in algebra. Are there any questions about any of these? This is really the meat of the course, this and the next couple of homeworks. We'll probably have an exam, a second exam on group theory in about 3 weeks, just a week or two before the final. But it's really important to learn this material. This is what most of the second exam will be on. Any questions? So really, you need to spend time studying the notes, studying the lectures, and making sure you understand the logic that goes into the problems, as well as the calculations we did at the beginning of the class today on calculating cosets of a subgroup of a group. Okay, well, all right. If there's nothing else, then we are done for the day. It looks like it's a beautiful day, so enjoy it. And be back on Wednesday.